Hey everyone, welcome to this explainer. Grab those notes and get dialed in, because today we're running a high-energy final exam prep bootcamp focused entirely on e-waste management. Whether you're an engineering undergrad, an IT professional, or really just someone who wants to understand the true life cycle of the tech we use every single day, you are in exactly the right place. We're going to lock in those critical concepts you absolutely need to know.
Here's our game plan for today. We're going to hit the theory toolkit, dive into some analytical scenarios, tackle a practice quiz, and wrap it all up with some final thoughts. Let's get moving.
All right, part one, the theory toolkit. These are the critical stats and frameworks you need to pass. We've got to start by understanding the sheer scale of the global e-waste crisis.
I need you to hit your mental save button on this number right now. 62 million tons. That is the exact amount of electronic waste we generated globally in the year 2023. It's a brand new record. To put that completely wild number into perspective, that's equivalent to the weight of 62 Eiffel Towers made entirely of discarded electronics, generated in just 12 months. E-waste isn't just a problem. It's currently the world's fastest growing waste stream, expanding at 3 to 4 times the rate of any other waste category out there.
Now, this breakdown is frankly alarming. Out of all those 62 million tons, a measly 17.4% is formally recycled. That means almost 83% is just discarded. It's tossed in landfills or handed over to informal recyclers. And you know what that leads to? Toxic open burning to expose copper wire and acid baths that just hemorrhage heavy metals right into our waterways. But beyond being a massive environmental disaster, this also represents a staggering $57 billion in lost raw materials every single year.
And that $57 billion loss? That brings us to one of my favorite concepts, the urban mine. Think about exactly what's inside the devices sitting on your desk. You've got precious, highly recoverable materials like gold packed into circuit board connectors and critical minerals like cobalt powering lithium-ion batteries. But on the flip side, you've also got toxic hazards like lead in legacy CRT monitors and conflict minerals like tantalum. Get this, the concentration of gold in e-waste is actually 40 to 80 times richer than what you'd find in natural gold ore. As engineers, we have to design with these materials and their safe recovery top of mind.
So, the big question is, how do we actually force the industry to care about this urban mine? The answer is EPR, or Extended Producer Responsibility. This is a crucial policy principle that makes manufacturers financially responsible for their products from cradle to grave. That includes the collection and recycling when that device finally dies. This completely changes the game for engineers. Why? Because when manufacturers suddenly have to foot the bill for end-of-life recycling, they instantly have a massive financial incentive to design products that are way cheaper and easier to dismantle.
Which perfectly illustrates our ultimate goal, moving away from a linear take-make-waste model and shifting to a true circular economy. In this preferred hierarchy, we prioritize reuse first. If we can't do that, we move to repair and refurbish, and then remanufacture. But look at what's sitting all the way at the bottom: recycle. Recycling is literally our last resort. We want engineers designing for repairability and longevity first, because keeping a device in use retains so much more of its embodied value and carbon footprint than just shredding it up for raw metals.
Moving on to part 2. Analytical scenarios. It's time to take that theory and apply it to real-world engineering decisions. I want you to pause, ponder the math, and apply everything we just covered.
Okay, let's put you in the driver's seat. Here's your first scenario. You're an engineer, and your design team wants to glue a phone battery securely in place just to shave a tiny millimeter off the device's thickness. Think about that circular hierarchy we just looked at. What is the actual real-world impact of that glue? And what should you, as the engineer, advocate for?
All right, let's break down the solution. If you glue that battery, you are entirely preventing user replacement, which happens to be the single most common repair to extend a device's life. When that battery inevitably degrades after 500 charge cycles, your user is probably going to just toss the whole phone rather than pay for a really complex, expensive repair. So you're effectively pushing the device directly from the use phase straight down to recycle. You're skipping repair entirely and completely destroying its embodied value. The right engineering choice here is to advocate for accessible battery design, which, by the way, now perfectly aligns with the EU's right to repair regulations.
Let's pivot to our second scenario, and this one is all about the procurement math. An IT department needs to swap out 100 computers. A vendor offers them brand new machines for $500 a pop, or certified refurbished machines with a solid warranty for $280 each.
Take a second. What should that IT department recommend to their leadership and why?
Let's look at the side-by-side math here. Buying 100 brand new computers, that's going to cost the org $50,000. But more importantly, manufacturing a new device triggers 70 to 80% of its entire lifetime carbon footprint before the user even turns it on. On the flip side, if you recommend the refurbished route, it only costs $28,000. You're saving the organization $22,000, you are dramatically reducing the embodied carbon by completely avoiding new manufacturing, and you're keeping existing devices in that highly valuable remanufacture loop. Honestly, it's a massive financial and environmental win-win.
All right, part 3, the final exam. Time for a practice quiz with detailed solution explainers. Let's shift into high gear and test your knowledge. Make sure you lock in your answers as we go.
Question 1. Globally, approximately what percentage of e-waste is formally recycled through certified processes? Is it 50%, 17%, 80%, or 5%? Make your choice.
If you guessed B, you nailed it. It's roughly 17.4%. Our system is basically broken right now. By completely ignoring that remaining 83%, we are literally throwing away or burning a $57 billion urban mine, all while poisoning our own environment in the process.
Moving to question 2. Imagine a 30-year-old CRT television is being tossed out. Think back to that urban mine toolkit we established a few minutes ago. Which toxic material is it most likely to contain in significant quantities, and what is the major health concern associated with it?
The culprit here is lead. These old legacy CRT monitors can literally contain up to 4 kilograms of lead right in their glass screens. When these end up in informal recycling clusters like the ones heavily documented in the Nimtoli and Islampur areas of Dhaka, Bangladesh, and they get improperly crushed, that lead leaches right out. It causes severe, irreversible neurological damage, especially in children living near those sites.
Question 3. What exactly is Extended Producer Responsibility, or EPR, and what is its single most important effect on product engineering? Think about those feedback loops we talked about. All right, here's the breakdown. EPR takes the cost of end-of-life disposal and hands it right back to the manufacturer. The engineering effect of that is absolutely massive. It creates a direct, undeniable financial incentive to reduce material complexity and ditch toxic materials, simply because doing so makes recycling much cheaper. It practically forces engineers to design for rapid disassembly. Just look at regulations like Bangladesh's e-waste rules of 2021. They're built entirely around this EPR framework to force way better upstream engineering.
Question 4. In the circular economy hierarchy for IT hardware, what action should an engineer prioritize first when a device hits the end of its useful life in an organization? What's step number 1?
The very first step is always evaluating for reuse or repair. Remember, recycling is literally our last resort. Recycling only recovers raw materials, and it burns up a ton of energy to do it. Reuse and repair, however, retain the device's embodied carbon, its manufacturing energy, and its full actual functionality.
And finally, question 5. This brings it all home to the device you probably have in your pocket right now. What is the actual truth about the materials packed inside a modern smartphone? The correct statement is that your phone is a literal, certified urban mine. A single smartphone packs in over 60 elements from the periodic table. We're talking gold, silver, copper, and critical battery minerals like cobalt and lithium. Just 1 ton of smartphones holds 40 to 80 times more gold than a ton of natural gold ore. This completely underscores why formal e-waste management isn't just a nice-to-have environmental initiative. It is a hardcore economic imperative. All right, you made it through the boot camp. But before we wrap this explainer, I want to leave you with a final, somewhat provocative thought to really chew on. The gap between formal regulations and the dangerous, informal recycling realities is just huge right now. So imagine you were tasked with designing an e-waste collection system for your university or your workplace. How would you design it to be financially self-sustaining? How do you actually capture that urban mine value to pay for safe processing? Really think about it, because solving that equation, that's the entire future of sustainable engineering. Thanks so much for joining me on this explainer, and keep learning.